Good morning and welcome to our lesson today. We are still on curved surfaces and we have been able to look at the types as well as how we can come up with them, how we can actually make our curved surfaces. Now, we want to go a step further and find out how light is actually reflected on these surfaces. Now, here, we want to consider four rays, and how they are supposed to be reflected in order for us to come up with the image of our interest. Now, these four rays are what we call the laws of reflection by curved surfaces. Now, our ray number one is a ray through C, a ray through C, or appearing to pass through C. Is a ray through C or appearing to come or to pass through C. Now, remember, if, for example, we consider the case of a concave reflector, we have the principal axis, and here we have our R. Here is where we will have our focal point, and here we shall have P. C is also called the radius of curvature, or we can even call it the center of curvature. Remember, we defined it as the center of that sphere of which our reflecting surface forms part. Now, we could consider a ray as the pole. This is F, this is C. Now, we could consider a ray of light that passes through C. So, in this case, we could have a ray of light passing through C and incident at a point on our reflecting surface, and we want to find out how is that ray reflected. Now, let us assume this is the direction. Let us assume that this is the direction of the ray. Now, we expect that it is going to be reflected through the same path. It is actually going to be reflected through the same path. Therefore, it is reflected through the same path. Through the same path. That means the direction when it falls on our reflecting surface, what is going to happen is that it will bounce back but maintain its route, maintain its original route. That is our law number one. Now, number two is a ray through F, or appearing to pass through F. Now, this is the second law, and we equally want to draw and find out how the same is going to be reflected. Now, we have our F here, then we have our C. Here we have the pole of the reflecting surface. Now, if we had a ray incident on our reflecting surface and through F like that, this ray is reflected in such a way that it is parallel to the principal axis, that the ray was incident on some point on our reflecting surface, and through F, which is our focal point, this ray is going to be reflected in such a way that it's going to be parallel to the principal axis, which again is this line that is joining the three crucial parts that we are considering. Now, it's good to note that it is reflected parallel to the principal axis. Parallel to the principal axis, in that it was incident at some point on our reflecting surface and it was passing through F. That's why the path now changes so that it traces one which is parallel to the principal axis. We could also consider another one, which is a ray close and parallel to the principal axis. A ray close and parallel to the principal axis, and this one here, that's the pole, that's F, that's C. Then we are talking about a ray close and parallel to the principal axis. This is our principal axis. So we want to consider a ray of this nature and find out how is it going to be reflected. And basically, it is reflected so that it comes, it traces a path through F. So a ray close and parallel to the principal axis is reflected to pass through F. It is reflected to pass through F. Now finally, the fourth law, or the fourth important ray that we are going to look at is a ray at an angle a ray at an angle to the principal axis. A ray at an angle to the principal axis. Let us, for example, look at a ray like this. So that makes an angle, let us call it a small I, with the principal axis. Now, in this case, we will realize that the principal axis is actually perpendicular to our surface of reflection. So therefore, if we take it to be our normal, this is the incident ray. We take our principal axis as our normal. Then this ray is reflected at an angle we are going to call small r there, so that now the laws of reflection are actually obeyed. So it is reflected in such a way that the laws of reflection are obeyed. It is reflected in such a way that the laws of reflection are obeyed. Need I remind you about the laws of reflection? We said that the three rays, let us take this one to be the reflected ray. Now, we said that for the laws of reflection to be observed, the incident ray, the normal, and the reflected, all of them should lie on the same plane. Now, in this case, we take our reflecting surface to be the plane, the reflecting plane, so that now we have the incident, we have the normal, and we have the reflected rays all on the same plane. Again, there should be a consideration at the angles I and R, so that I should be equal to R. So our ray is reflected in such a way that the angle of incidence and the angle of reflection are actually equal. So basically, those are the laws that we have in as far as a reflection by plane or by curved surfaces is concerned. We have looked at 4, a ray through C, which is reflected along the same path. We have also looked at another one, which is incident through F, which is actually reflected so that the path will be parallel to the principal axis. We have a ray close and parallel to the principal axis. That one is reflected through F. And then finally, we have looked at a ray at an angle, and we have found out that the ray is actually reflected so that the laws of reflection are actually observed. Now, we want to look at the principle of reversibility of light. Principle of reversibility of light pulse ray diagrams. Before we look at the law of reversibility of light, let us consider some ray diagrams. And a ray diagram is actually drawn. It is drawn to show the following. A ray diagram is supposed to help us to trace an image of an object formed by reflection of light using a curved surface. Remember, we said that we are after those images that will be formed when light is reflected by our curved surfaces. Now, in this case, these images are going to have different characteristics depending on the position of the object relative to our reflecting surface. But basically, a ray diagram should show the following. Number one is the position of image formed. Position of image formed. Number two is the nature of the image. Nature of the image. In this case, we will ask ourselves, is it real or virtual? Is it real or virtual? Number three, we will talk about the size of the image. Is it enlarged or diminished? Remember here, all these characteristics are emanating from our comparison between the object that we have and the image formed. So we are going to look at these aspects relative to the two. Number four is the posture of the image. Posture of the image, we are going to ask ourselves, is it upright or is it inverted? Is it upright or inverted? Therefore, for you to be in a position to actually describe the image formed by these curved surfaces, you ought to consider the four. Number one is the position of the image. Number two is the nature. You will require to tell us whether it is real or virtual. Then you can look at the size of the image relative to the object. Find out whether it is smaller than the object or whether it is larger than the object. In some cases, the images will be larger than the object. And finally, you will consider the posture of the image, where you will tell us whether the image is real or virtual. Now, let us take an example so that we can see how we draw these diagrams. We note objects, number one, objects and images are represented using arrows whose tip or head shows the top. So therefore, if you have an object, you are not going to draw the actual diagram. You will just use array, where now this one will show the top or the head of the object, and then this one should be the tail. So for an upright image, the arrow will point upwards, and for an inverted image or object, the arrow will change direction. Now, point number 2 that you should have in mind is that images that are real are represented using a continuous arrow, while the virtual ones will be represented using a dotted arrow. So, dotted lines and rays show virtual images and rays, while continuous ones are actually real. Take an example of something like this. If you had your object represented using an arrow, and then after resolving your ray diagram, you find that the object formed is actually virtual, you are supposed to use dotted lines. A dotted arrow will show us whether your object is virtual or whether your image is virtual or not. Sometimes you could have upright virtual images. You use dotted arrows to show the same. Now, let us consider the following ray diagrams. Let us consider the following ray diagram. One, object at infinity. Object at infinity. Then we shall have our reflecting surface. We have our principal axis with our F. Then we have our C. We have our C. Then we consider an object at infinity, so that now we have some rays coming from a distant object. Now those arrows are incident at an angle to our reflecting surface, and we said they should be reflected in such a way that they are supposed to have the same angle. Let us draw some normals. The angle of incidence should be equal to the angle of reflection. Therefore, you will have something like this, so that this angle here, let us call it R1, I1, so that now I1 will be equal to R1. Now again, if we had a normal here for our second ray, we have I2, which is the angle of incidence, number 2. We also need to reflect our ray in such a way that the angle of reflection will be equal to the angle of incidence. So we have something like that. So that we have R2. So in this case, I1, I2 will also be equal to R2. Therefore, we have some image here formed at the point of intersection. Remember that the point of intersection is the tip of our image. Therefore, we will have something like this. This is our image. So our object was distant. That is why we said it's actually at infinity. Then our image is formed. Now look at number 1, position. For the position, you say it's actually between F and C, that our object is between F and C. Number 2, you note that our object is on the same side as the image. Therefore, we talk about the nature. Again, nature of the image is that our image is real because it is on the same side as the object. Number 3, you will talk about the size. And you will say that our image is actually diminished. It is diminished because it is smaller than the object. And finally, you will talk about the posture. The posture, where you will say that it is actually inverted. So, by looking at those 4, you will actually have described your image fully. Remember, it was at infinity. We were actually observing a distant object. We had some 2 rays which were incident on our reflecting surface. We used the 4th law, where we reflect the rays in such a way that the laws of reflection are actually obeyed. In this case, we considered the angle of incidence. We made sure it is equal to the angle of reflection for the 2 rays. Therefore, we had these 2 as our reflected rays. Then we went on to trace our object, where now our image, where now we looked at the point of intersection of the reflected rays, which forms the tip. Draw your image, then describe it using the 4 aspects of the image formed. Now, we consider another one. We consider another object. In this case, we can put it at C. This is number 2. Object at C. We have our principal axis. Remember, this is the pole. Again, we have our F here. Then we have C. And at this point, we want to place a real object at C here. We want to place a real object at C and see what we can say about the same. Now, number 1, we consider some 2 rays from the laws of reflection by curved surfaces. Let us consider a ray from the tip, probably parallel to the principal axis. This one. It's incident on our reflecting surface and parallel to the principal axis. Remember, we said this one is reflected through F, like that. It is actually reflected through F, and then we can consider another ray, probably through F, like that, and from the tip parallel to the principal axis, it's going to be reflected in such a way that it will pass through F. So we have that kind of a reflection. We can also consider another one, which is through F, and this one is reflected in such a way that it is going to be parallel to the principal axis. So that now we have the point of intersection at C. So that now we have our image like that. Now, we cannot leave our diagram like that. We need to go ahead and describe the image that we have formed. And we start by looking at the position. The position, we can say that the image is formed at C. Like you can see, it is formed at C. We say something about the nature of the image. You can say that the image is actually real. Then you go to the posture. a posture, and clearly you can be able to observe that our image is actually inverted. It's inverted. And number 4, which is the last one, we could talk about the size of the image, and say it's the same size as object. Therefore, it is a must for us to consider the 4 aspects for us to have described our image fully. Talk about the position, talk about the nature, the posture, and finally you can talk about the size. Therefore, basically we are picking on any 2 rays so that we can make them intersect at some point, which will form the tip of our image, and then we can go ahead and draw our image as well as describe it using what we can see. So there's no need for you to memorize. You just actually look at the diagram, draw it correctly. If possible, you can draw it to scale, and then you can consider the characteristics that you can actually see. Now, let us consider another ray diagram. Let's consider another ray diagram. This time, object beyond C. Object beyond C. Here we will have our reflecting surface again. Then we can have our principal axis. We can show the position here of our F. Then we can have our C. Then this is the pole. Then somewhere beyond C is where we want to place our object. So we can put it here, for example. We can put our object there. And then we can try and trace the image of that object using some rays. Let us consider the most common one, which is the ray parallel to the principal axis, this one. And we agreed that is going to be reflected through the principal focus. So we are going to have something like that. Then we can consider another one. This time, let us consider something like a ray through C, through our C here. And which is reflected along the same path. This ray is actually reflected along the same path, so that we are going to have something like that. Now, when it is reflected like that, this one forms the tip of our object. That's the tip of our image. So that now, if this was the object, this one becomes the image. Then, after drawing that, we can go ahead and come up with characteristics of this image of ours. Number 1, we can consider the position position of the image and say that it is located between C and F. It is actually located between C and F. Number 2, say something about the size. In this case, we want to compare the size of the object relative to that of the image, and we will find out that actually the object is diminished. It is actually diminished. In other words, we could say it's smaller than the object. Number 3, we can talk about the nature of the object, where we note that nature of the image, where we note that it's actually a real image. It's real. Number 4 is the posture. And clearly we can see that the image is actually inverted relative to the object. It's actually inverted. The image is inverted. The image is inverted. Let us look at another one. This time we consider an object which is actually placed between F and C. Find out what we can say about its image. That is an object between F and C. Object between F and C. We can place it somewhere here. We can place it somewhere there. Then we find out how the image is going to be. How the image is going to be. Consider this ray. This one. We consider a ray that is actually parallel to the principal axis. Remember, this one is our principal axis. Then we have our object between C and F. Therefore, we want to find out this one, this ray, how is it going to be reflected? And we noted that it's going to be reflected to pass through F, like that, to pass through F. Then you could consider a ray through F, a ray through F, a ray through F incident to our reflecting surface, and this ray is actually reflected parallel to the principal axis, parallel to the principal axis. Now, where they meet, their point of intersection, actually is the tip of our image. So in this case, we are going to have an image that looks like that. Now, by now, we should have known how to describe an image So let us go ahead and try to describe the same. Number one, talk about the position. The position, we have our pole, we have our F, we have our C, and then the image comes behind C. So we are going to say that our image is formed beyond C. That is where our image is located, beyond C. Number two, let us talk about the size of the same. And what is the size of our object relative to the image? We can note that it is actually enlarged. It is enlarged. By enlarged, we mean that the image is actually greater than the object. Number three is the nature of the image. And the nature of the image, what we can see is that the image is actually real. And finally, we can talk about the posture. That is the posture. And the posture is actually an inverted image. Therefore, those four are the aspects that we can actually be able to use to describe our image characteristics. That for the position, it's beyond C. For the size, we can see that's bigger than the object. For the nature, it's actually real. And for the posture, it's actually inverted. Of an object at F, and see how we are going to describe the same. Now, put our F here, our C here. Then our object is placed at F. Let us consider some two rays from the laws. This one is the first one, which is parallel to the principal axis. Let us reflect it through F. Then we can consider another one, which we consider a ray that is parallel to the principal axis, and then we will reflect it through F. Then we can have a ray through C, a ray through C, yes, we consider another one which is through C and which is supposed to be reflected along the same path. Now, clearly, you can be able to see that these rays are actually parallel to each other. The reflected rays, are actually parallel. Now that means that our image, if we go to the characteristics of our image, is that it is at infinity. the image can be formed anywhere. It is actually at infinity. And now that we cannot be able to trace it, we cannot talk about the posture, we cannot talk about the size, we can also not talk about anything else apart from actually the position. Therefore, that is all we could say. We cannot even describe the nature because we can't actually trace the image. And finally, let us talk about an image. Number 5, let us try and trace an image of an object placed between the pole and F. An object that is actually between F and P. We can also draw it. If this is our F, this is our C, and this one is our pole, then we can place our object somewhere here. There. How is it going to be formed? How is the image going to be formed? Let us look at this ray here, which should be reflected through F. Then we can have a ray through C and the tip of the object, so that we can extend our rays. Then we can have one through C. Again, we can extend it so that now it is reflected along the same path. We have considered the first one, which is the ray parallel to the principal axis, which is supposed to be reflected through F. Then we have this one, which is actually through C and the tip of our object, and we expect it to be reflected along the same path. Now, these rays are going to be, they are going to intersect somewhere behind our reflecting surface. That is to mean that our image is going to be in the opposite side of the reflecting surface as the object. Therefore, we can try and describe it. Number 1 is the position. The position of the image is behind the curved surface. Behind the curved surface. We could talk about the size, and we can say it's enlarged. Posture is that it's actually upright. And number 4 is on. It's upright, enlarged behind the curved surface. And then number 4 is the nature. Nature, where we can be able to say that actually our image is virtual. Our image is actually virtual. Now, the diagrams we've been drawing are those of a concave reflecting surface. And we've not said anything about images formed by convex reflectors. And basically, we have been able to find out that the position of the object is very important in as far as the image position and other characteristics are concerned. Now, for a convex reflector, now, regardless of the position of the object, the image will always exhibit the following characteristics. It will always be upright. It will always be between F and P. And number 3, it will always be diminished. That for a convex reflector, the image, regardless of where you place your object, the image will always be upright. It will always be diminished. It will always be between F and P. And finally, it will always be virtual. Will always be virtual. And for that reason, we do not actually study the images formed by convex reflectors. Now, let us look at the law of reversibility of light. And in this case, we want to find out, can light trace its own path again? Can light trace its own path again? Now, we consider a concave reflector. And for a concave reflector, this being our F, our C is somewhere there, and then we have our pole there. Now, these rays that we are considering are rays through F. The direction of travel is through F to our reflecting surface. Through F to our reflecting surface, like that. Now, from the law of refraction, they should trace a path parallel to the principal axis after reflection. Now we have looked at the law of reversibility of light. Now we have looked at the law of reflection by curved surfaces, and we have said for a concave reflector, rays that will come from some distance through F are supposed to be reflected in such a way that they are going to be parallel to the principal axis. Now note that for this reflector, C and F are real. That is why we say that rays of light will actually pass through F and C. Now, as we shall be able to find out with the convex reflectors, is that C and F are actually virtual. So that is why we say the rays appear to come from these particular points. Now, suppose we reversed the directions. Suppose we reversed the directions so that now we have a beam of light parallel to the principal axis. So that we have a beam of light parallel to the principal axis. Now, suppose we reversed the direction of travel of our light so that now the rays that we have are incident to the reflecting surface and parallel to the principal axis, like we have in the diagram. Remember, here we have our pole, here we have our C. Now, by the law of refraction at curved surfaces, rays parallel to the principal axis are reflected through F. That we now have a beam that is parallel to the principal axis, and now the rays are going to trace some path like that. They are going to be reflected in such a way that they will pass through F, like we have on our diagram. Now, that means that light can actually trace its own path again, that the path of light is actually reversible. That by reversing a direction of travel, rays trace their original path. They trace their original path, and that implies that actually the path of light is reversible. That initially we had a beam through F. Remember that this one is a converging surface. We had a beam through F, and then it was reflected in such a way that it traced paths which are parallel to the principal axis. Now this time we have actually reversed the direction of the rays, and now we have considered a beam that is parallel to our principal axis, and they have been reflected so that they converge at F before diverging again. That means that the path of light is actually reversible. Now, there's something interesting about the concave reflector that we need to find out, and it's actually about C and F. Now, for a concave reflector, rays will actually pass through the two points when they are required to. They will pass through F and they will pass through C when they are required to do that. Now, as we are going to observe with the convex reflector, F and C are actually virtual. That is why we say rays appear. They actually appear to diverge from that particular point. They diverge from that particular point. Now, if we consider a convex reflector, now a beam of light that is parallel and incident on the reflecting surface is actually reflected so that it appears to come from some point behind. Remember we said that this one actually diverges. It scatters. It actually scatters the beam. Therefore, the rays of light after reflection will not actually pass through the principal focus, but they will appear to pass. Now, remember this reflecting surface is part of a sphere. And if we trace the sphere of which the reflecting surface is part, you find that these points are actually inside, on the opposite side of the reflecting surface, which means that it's F and C are virtual. That for a diverging kind of a surface, F and C are actually virtual. Therefore, our rays will not pass through F and C because they are reflected on the outer side, but they actually appear as if they are coming from some point F behind the reflecting surface. We could consider a reverse of those parts so that we consider now a ray that is divergent on the surface and see how it is actually reflected. We reversed the same path and we used the same reflector. We will find out that these rays which appear to converge at some point F are going to be reflected in such a way that they are going to be parallel to the principal axis. Remember that our reflecting surface is the outer, the other side. The reflecting surface is on the outer side. Therefore, if our F is here and our C is there, our pole is equally there, they still remain virtual. Therefore, our rays are not going to pass through these points, but actually they appear to pass through them. Therefore, that is why we use the dotted lines, which means that our rays are actually virtual, and that if we reversed the direction of incidence, we can still trace the original parallel paths of our rays. That is to mean that actually you can reverse the direction of a ray. For that, we come up with the law of reversibility of light, which states that a path of light is traceable. A path of light is actually traceable. You just need to reverse your light and you have your original direction of motion of rays. That brings us to the end. Next time we meet, we talk about the mirror formula. Thank you.